In section 5.2, we're going to be learning about the technique of calorimetry. Calorimetry is a technique for measuring the amount of heat that is either absorbed or released during a chemical or physical process. And basically what we're going to do is, it's difficult to measure these processes directly, so we're going to place them inside of some sort of medium that we can measure the temperature of very precisely. And we're going to then figure out how much this chemical process has either raised or lowered the temperature of that medium. And we're going to do this inside of a device called a calorimeter. And we're going to need to calibrate our calorimeter so that we know how much heat is required in order to raise the temperature by a certain amount or lower the temperature by a certain amount. So first we're going to start with a couple of definitions. We have the system. This is the chemical or physical change that we're interested in measuring that's going to be difficult to measure otherwise. And then we have the surroundings. This is all the other stuff that's around in our calorimeter that we are going to be able to measure the temperature of. So we're going to see a transfer of heat from the system to the surroundings, or in the case of an exothermic reaction, or we're going to see a transfer of heat from the surroundings to the system in the case of an endothermic reaction. We can picture that here, where we have our system releasing heat in an exothermic process, and that's going to go out to the solution that it's being suspended in, which is our surroundings, and then that's ultimately going to come to some thermal equilibrium. Or we're going to have the case where the system is undergoing an endothermic reaction and heat is moving from the surroundings into the system in this case. Eventually that goes to thermal equilibrium and the temperature of the surroundings has gone down. So what makes a good calorimeter? Our calorimeter has to be really well insulated. All the heat that is either released or absorbed, everything about our system and surroundings has to be insulated from the outside world. We can't let heat escape and we can't let it get inside our calorimeter. A lot of the times you'll see the classic experiment is the coffee cup calorimeter. This is where we just use like polystyrene cups to create a calorimeter. Here's an example of that. You can see you just kind of double up on the polystyrene cups and you fasten a little cap of some sort to the top there so that you don't have heat coming in and out here. We can measure the temperature with a regular thermometer, and we have this little stir. They put this little loop on the bottom so you don't hit that, and you just kind of work it up and down. Calorimeters can be quite a bit fancier than that though. Here is kind of a analog to a coffee cup calorimeter. That's a commercial unit. It's made out of two concentric vessels that have a little air gap in them here, and that's causing the insulation. Still just a insulating cover, thermometer, and a stirrer there. Here we have something that's a little fancier than that. It's a little bit larger, still using kind of an air gap for insulation, but this one has a little mechanical motor here that's turning this guy, so it's continuously being stirred. And then you can put in a electronic thermometer here. This is called a thermocouple. And you can measure, some of these are very nice. You can measure very small amounts of temperature change down to the thousandths place or more. So let's think about what's going to happen here with a kind of basic example. Let's consider that we have a hot piece of metal, we're going to call it M, and a cool water, W. If the metal is placed in the water within a calorimeter, so it's completely separated and isolated from the surroundings, heat's going to transfer from the metal to the water. The temperature of the metal will decrease, and the temperature of the water is going to increase. And then eventually they're going to come to thermal equilibrium, where they both have the same temperature. In a scenario like this, the heat released by the metal plus the heat gained by the water is going to sum together to be 0. These guys have opposite signs, so we can see that the heat of the metal is going to equal the negative heat of the water. They're going to have the same magnitude but different signs in this case. If we kind of picture what's happening here, we've got our metal inside of our calorimeter, that's our system. Heat's being released out to the water, which is our surroundings. Eventually they come to thermal equilibrium, and we can see that the thermometer's temperature has risen up because the water, the thing that we're actually measuring, got warmer. Let's see how we can actually put numbers to this, though, and quantify this. So if we have a 360 gram piece of rebar, this is like a steel rod used for reinforcing concrete. You've probably seen these before. And we drop that into 425 milliliters of water that's at 24 degrees C, so roughly room temperature. The final temperature of the water is measured to be 42.7 degrees Celsius. And we want to calculate the initial temperature of the piece of rebar. And we're going to make some assumptions here. We're going to assume that the specific heat of steel is approximately the same as that for iron. And we could find that value in table 5.1 in the textbook. And that all the heat transfer occurs between the rebar and the water because we have some insulation around it. So the first thing that we need to recognize here is that the heat lost by the rebar is going to be gained by the water, and therefore Q rebar is going to equal negative Q water. Since we're going to substitute in our definitions for heat, so we have the specific heat capacity of the rebar, we have the mass of the rebar, so we could look up the specific heat capacity for steel in table 5.1 to get the specific heat for the rebar. The mass of rebar was given to us in the problem. The delta T of rebar is part of the question that we're asking. We knew its initial temperature, or final temperature, but we don't know what the initial temperature was. Then we're going to have our C for water. This is going to be that 4.184 number that we were working with before. The mass of water was given to us in the temperature, and the initial and final temperature of the water was also given in the problem. If we expand out our delta T values here, we get this expression here, which looks a little complicated, but we now know pretty much all of these values except for the initial temperature of the rebar, which is what we wanted to know. So if we start plugging in all those values, the one that we got from table 5.1 for the specific heat of the rebar, the mass of that rebar, its initial temperature or final temperature, which is going to be the same as the water, because remember they came to thermal equilibrium, right? And then we have the specific heat for the water, we have the mass of the water, we know that the water was initially at 24.0 degrees Celsius. Now all we need to do is some algebra, right? We're going to have to distribute these values through here. We're going to have to gather all the terms with Ti on the other side and then divide through. We can determine that the initial temperature of the rebar was 248 degrees C. And that was the initial temperature of the rebar. I have an example in the homework problems where I go through the algebra to do these kind of problems. So if you're a little curious about that, you can check that. So in our example before, we weren't doing calorimetry. properly, right? But we can see that we can extend the exact same principles to actually doing calorimetry, even if we're mixing solutions, and it's not necessarily completely clear where the system is, like it was in the example with the metal. So let's take a look at an example here of that. When we are mixing 50 milliliters of 1 molar HCl and 50 milliliters of 1 molar NaOH, and both of those solutions are at 22 degrees Celsius, we add them into our coffee cup calorimeter, and the temperature of this mixture reaches a maximum of 28.9 degrees Celsius. So in this case, our system are the molecules of HCl and NaOH that are combining together to form NaCl and water. We can't see it like we did with the metal before, but the math behind it is exactly the same. So we're going to have that our Q reaction, the heat given off by this reaction, is going to be equal to the negative Q of the solution. We're going to input our definition for heat into Q solution. We're going to have the specific heat capacity of the solution times the mass of the solution times the temperature change of the solution. And now we're going to make a couple of assumptions here. So our first assumption is that 1 molar HCl and 1 molar NaOH, they have a specific heat capacity that's roughly the same as water, 4.184. Given that most of these solutions, most of the atoms in that solution are water, it's not unreasonable. It's going to be very close to that value. We're then going to also make the assumption that those two solutions have a density of about 1 gram per milliliter. So the 100 milliliters that we have altogether, 50 mils of HCl and 50 mils of NaOH, is going to weigh about 100 grams. And then we have our change in temperature, which is going to be the difference between that final temperature when we mix the two together and the initial temperature that they were both sitting at, 22 degrees Celsius. If we do all that math out, we're going to see that that reaction released 2.9 times 10 to the 3 joules. We do need to remember, though, that that was the Q for, or that we were looking for Q reaction, right? This was an exothermic reaction, so we should be getting a negative value, right? Heat was released from the system and into the solution. Q reaction equals negative Q solution. We get negative 2.9 times 10 to the 3. So bomb calorimetry. This is pretty useful in the sense that you can basically make almost anything combust completely given the right conditions. And so it's a good way to be able to do calorimetry with things that aren't necessarily going to react very quickly or easily in any kind of sense. And basically what we're going to do is we're going to take a vessel that they call a bomb. It's usually made out of very thick metal alloys, very tough little guys there. And we're going to charge that up with a whole bunch of oxygen. So like something like 25 atmospheres typically of oxygen would go into these little bombs here, okay? So that's just waiting to burn up. And you'll put your sample in a little cup like this. And then there's these two electrodes, and that's going to like make a little spark. So you put the two electrodes kind of close to the cup, and with all that oxygen in there, you ignite it, and it burns this up completely. And then the vessel heats up, and the water heats up, and we can figure out how much energy was inside of that sample. This is what they do often with things like food or fuels and stuff to figure out how much energy is going to be released. Another example of a calorimeter is a whole body calorimeter. It's like a giant calorimeter that they put people in and basically measure how much energy is coming off of them, given how much food that they ate. And in this sense, they come up with a value that's known as the nutritional calories. So you eat a certain amount of energy, but you don't necessarily use it all. Some of that food just goes completely unwasted and goes right through your body, and it never really gets burned as fuel inside your body. So they have this idea of the nutritional calorie, which is the energy unit used to quantify the amount of energy derived from the metabolism of food.